Alright, 17 it says we have a rectangle that's got one side on the x-axis has its upper vertices in the graph of y equals cosine x. And we want to know what is the minimum area, what was the minimum area of the shaded region. So ultimately, in our picture that we have here, got one arch of the cosine function. We got a rectangle here, and so I guess the question to ask here would be what would be the, if that dark area were to be a minimum, what would be the case of the white part, if you will? Wouldn't we want that to be as big as possible? No. So we've had these before where we have a rectangle inscribed here, and ultimately the dimensions of the rectangle, if we call that x, and we call that dimension cosine x, which is what it is because that's the height of it, it's determined by where we are on the curve. And so ultimately if this is a 2x by cosine x rectangle, then the area for it would be exactly what I just said, 2x cosine x. Okay. And if we wanted to find the maximum area here for that, maximize it, we would find the derivative. So we go first times the derivative of the second, plus the second times the derivative of the first. So we'd ultimately get negative 2x cosine, or negative 2x sine x, plus 2 cosine x. And ultimately we'd want to know when that equals 0. So again, we could use some algebra to solve that if we so chose, but ultimately we got a calculator, it's a calculator problem, so I would put that in my y equals and see when that equals. When that equals 0. Keeping in mind here that the x's in question here should be positive, number one. I mean, the x value is negative, it wouldn't make too much sense, I suppose. So let's go from 0 to, and to keep in mind that as far as we could go over here is where cosine hits the x-axis again, which would be pi over 2. So we can put pi over 2 as our max. And let's see what we see. So it looks like there is a point where it does equal 0. Keep in mind you also have a picture that guarantees that it's a maximum here because the derivative that we're looking at here goes from positive to negative, indicating a maximum for the function. So let's find that point. Try that again. Oh, I used the right command. How about using the 0 command? So we get 0.8603. And if we use that as our, and again, if we're going to use this to make any kind of calculations, I would take all the decimals down, of course. Right? So that's the x in question, and we know it's a maximum because of that, so we don't really have to do any testing. It's multiple choice anyway, so there'd be no, ultimately it's our only option, so we're assuming that it's not some kind of trick question, which it's not. Alright, so ultimately the question then is if that gives us, if that x gives us the maximum area, okay, what is the maximum area? Well, if I go 2 times 0.86033359 times cosine of 0.86033359, I get that, 1.1221926676. Right? So that's ultimately my area. Now, the question is though, is that the answer to the question? I mean, ultimately it's the area of the white rectangle, isn't it? So what are we going to have to do with that in order to get the area of the shaded part? Subtract it from what? Can we subtract it from negative pi over 2 to pi over 2? Cosine x dx. Wouldn't that be the area of the entire arch, if you will? If we subtract the white part. So, again, it's a calculator problem, so let's do it with the calculator. .76. Okay, .877 or 878 nearest thousandth, which corresponds to letter B. Questions on that one? AB or BC? The AB problem, it's maximization. What else? Through 19. 16, we have f as a differentiable function at a, and we know which of the following could be false. Part A says that f is continuous at a. Okay, keeping in mind we know it's differentiable here. Okay? So the question is, could we have discontinuous and still be differentiable? No. Okay. If you have something that's discontinuous, okay, like an asymptote or a pole or a jump discontinuity or an oscillator discontinuity, whatever the case may be, okay, can't be differentiable there. So that means, and again, keep in mind it says that which one could be false. Okay. Ultimately, A can't be false. Okay. We know it's differentiable, has to be continuous. Okay. How about part B? The limit exists there. Well, we couldn't have said yes to part A if B wasn't true. So B is still good. If it's differentiable, does that limit exist? Well, that limit is the derivative, isn't it? So since we know it's differentiable, then that is true. The derivative is defined. Okay. If it's defined, that just means it exists, right? So that's good. And then what about the second derivative? Could the second derivative not exist at a particular point where there's a derivative? Does it have to have a second derivative there? Doesn't have to, does it? Okay. So again, which one could be false? It could be false that there's a second derivative. Okay. All those other things are musts. And ultimately that AB problem as well. Okay. Just F prime, F double prime relationships. Also a definition of continuity and differentiable. What else up through 19? Okay. Okay, on 18 we have a, it says a solid has a rectangular base that lies in the first quadrant. It's bounded by the x and y axes and the lines x equals 2 and y equals 1. So if we look at a picture here, x equals 2 is going to be here, y equals 1 is going to be here, the x and y axes. So ultimately we're looking at this rectangle here. Alright, so if we have this rectangle, and it says the height of the solid above the point xy is 1 plus 3x. Okay. And it says which of the following Riemann sum approximation, which of the following is a Riemann sum approximation for the volume of the solid. Alright, so let's keep in mind here that that when we have this particular region, this is the base, of course, in the xy plane, and the shape is going to be coming out of the paper at us, if you will, again, kind of like we had that square one a minute ago. And what it boils down to is it says that the height of this solid, okay, is given by, or at any point xy is given by 1 plus 3x. Okay? So if I were to just pick a random point, let's say for instance, like let's say 1 and 1/2. Okay? Keep in mind again the height is 1 plus 3x at that point. So how far out of the paper would this come? It would come, again, if I'm at 1 and then half, okay, it would be at, the height here would be 4, wouldn't it? So in fact all along here, all along that vertical line, wouldn't the heights be 4 all along that thing? And as we go from left to right, keep in mind the height at the origin, and at any point that has 0 for x, the height is going to be 1, isn't it? So if you can kind of picture that, from a sideways standpoint, as we go up, it's going to be, kind of something like this, isn't it? If we were to look at it cross-section wise as we move to the right, here's our height at the origin is 1. Our height at 2 would be 7, if you will. True? Okay. So just to visualize what kind of shape we're dealing with, I guess, here. Let's go with that. All right. So the question, though, remains is what are we going to do then with this? How are we going to find a Riemann sum that will give us the actual volume of this shape? Okay. Well, let's think about as we go from left to right in this interval. If we were to write an integral for it at some point to sum up, I guess the question is that as we go from left to right, these heights, what are these heights like? Or in other words, can we come up with an expression for essentially the area of a slice? Keeping in mind that if I just take a slice right here, if you will, all right, that height of that slice is going to be determined by this. True? So the height of that slice is going to be determined by this. And remember, all along the entire vertical, if you will, it's coming out of the paper at exactly the same height because it doesn't depend on where we're at in the y direction. Okay? So really, isn't it going to make a rectangle, if you will? Wouldn't that be a rectangular slice if I took this thing and I sliced it? It's going to be a rectangle. So let's see if we can come up with an expression again for the area of that rectangle. Well, one dimension of the rectangle is right here that we have drawn on our paper. It's 1, isn't it? No matter where we are, that slice is going to be 1 in that direction. Okay? And then the height is going to be given by 1 times 3 plus x. Okay? And the thickness of each slice is going to be dx. So those are going to be representative of the dimensions that we have here. Okay? And then if we wrote an integral here, we'd go from 0 to 2. And if we integrate that, that would be our formula. Alright, so question is then, if we look at the different Riemann sums that are available there, okay, which one is essentially giving us the same information, I guess. Alright, and if you look at the choices that we have here, if we have this first one, if we have 1 over n, and then 1 plus 3i over n, okay, you'll notice the difference between that one and the second one is just that they've doubled it in the second one. And the third one, the third choice is instead of 1 over n, it's I over n. Okay? And then the last two choices are using this 6i over n. All right. All right. So I'm going to tell you right now that I'm going to basically take this question out in terms of your scoring. So I'll give you another point on that if you got this one wrong. There's a fact in here that we need to revisit in the book if this is going to be on there. I actually didn't notice this was even on here, because this one comes from a part of the section that we kind of skipped, because as far as I knew there wasn't problems like this on there. I asked when I went to the conference last time, I asked people if this kind of problem was going to be on the AP test anymore, because it used to be on there, but then there's been nothing about it since. And everybody agreed that there's not going to be one on there like that. So therefore, we didn't do this part in the book, okay, where you write the Riemann sum in more general form. So for the time being, I'm going to stick with the fact that it's not going to be on the AP test and that we don't have to worry about it. Okay. However, I'll do some more investigating and see if the people that I talked to are in fact wrong. If they're wrong, then we'll go back and revisit that so we can make sure we know how to do that. So for the time being, we'll just leave it alone, because I don't want to go through the whole lesson right now of how to start from scratch and do that. Make sense? All right. So just keep that. We'll just, like I said, we'll save that for later, if need be. Otherwise, if we deem it's not necessary, then we won't revisit it, because it would be unnecessary. All right. What else? All right. How about the other half? 20 through 24. In 19 we have 3 graphs that are labeled. This is one graph is a graph of f, one is the graph of f prime, one is the graph of f double prime, and which of the following have it correctly identified. So instead of redrawing that picture, so my art will not be very good. We ultimately have our options here, keeping in mind that when we're looking at relationships between graphs that are graphs of functions, derivatives, and second derivatives, we want to look at the behavior of the graphs in terms of their increasing and decreasing and try to relate that to our positives and negatives. So let's just say for 1, for example, if we look at 1, its behavior, it's decreasing until this point. True? Which means that its derivative had better be negative to that point. And then keep in mind that again it gets, the derivative is positive, the derivative of it is positive from there on out. So that means that if we have a picture of this one's derivative, okay, it should change from positive to negative, shouldn't it, at this point? And do any of those change from positive to negative? No. So that would kind of lead us to believe that this is probably not f, and it's probably not f prime either, is it? True? Because if it were f prime, then its second derivative would be available also. So that one doesn't appear to be either f or f prime, so we have fairly good reason to believe that the answer here is either d or e at this point. Alright, so let's look at number 2 here, which is this lightly dotted one. This one's behavior is it's positive to get to here, negative to get to here, and then positive from there on out. Okay, so the question is, which one of those other 2 curves has y values that correspond? Should have positive derivative, negative derivative, positive derivative. Isn't it this one? Positive values, negative values, positive values. So ultimately that would tell us that 1 is the derivative of 2. So we get to handle that at this point. 1 would be the derivative of 2. Okay. And so if that's the case, then at this point with our choices here, we're looking at choice E would be the right one, wouldn't it? Okay. And just to double check, just to make sure, if we look at choice 3 here, the derivative here is negative all the way until we get to here, and then it's positive. And if you look at number 2, the values are negative, and then when you get here, the values become positive. Which again, the derivatives of 3, the slopes of 3 match up with the values of 2, which makes 2 the derivative of 3. So the original function then is 3, the derivative is 2, and the second derivative would be 1. And also too, keep in mind that where 3, notice that 3 is concave up here in this area. What are the values of 1 like? Positive, which makes sense also, doesn't it? Okay. What else? On 20, we have a v of t function, natural log of t plus 1 minus 2t plus 1. And it says if this is our particle moving along the x-axis time greater than 0, we want to know what's the total distance traveled. And remember, again, keep in mind this is a calculator problem because we could do this by hand likely, but we don't really need to because we have our calculator available. So if we do natural log of x plus 1 minus 2x plus 1, go 0 to 2. So I'm going to do that, and then I'm going to ask, why is this not necessarily the answer? Remember, this gives us displacement. This gives us our change in position over that time frame. Okay? We don't want displacement though, we want total distance traveled, which means that we need to add in, instead of that integrand, it needs to be the absolute value of that. So if we insert an absolute value, and our parentheses, now we get the total distance traveled, which would be 1.54, etc. Should correspond to letter C.
do we use the integral of the square root, the derivative of that whole formula?
That's the curve length.
Oh, okay.
Yeah. So yeah, this problem is just it's an A/B problem. Just we want total distance traveled. Ultimately, I guess another instance where we'd use total distance traveled on something like that, where if we had a particle that moves along some curve, if you will. You know, if I had a curve that looked like that, and we want to know the distance traveled of the particle on the actual curve, and it was generally defined parametrically, right? That would be a total distance problem where we're finding curve length essentially. Okay? But if we just have a particle traveling along an axis, okay, the total distance is just the integral of the absolute value of the velocity curve. But again, key is that we got to make sure that we do the absolute value part, get the total distance traveled. What else? Yeah. And 21, we have function f defined by the cube of x plus 2, the square root of that. And ultimately, this is we just did two of these earlier. It's that same problem basically when we write f of t instead. And we go x cubed plus 2. And our initial condition is 3, 5, so we go 3 to t and then plus 5 on the end. And then once we have that written, now we can put our 1 in there and just calculate. What else? No. We got this g function this time is 100 plus 20 sine of pi over 2t plus 10 cosine of pi over 6t. Alright, and the bottom line here is it says that on the interval 0 to 8, g is decreasing most rapidly when t is equal to what? So remember, increasing and decreasing most rapidly is a matter of thinking about, let's say this is increasing. Okay, it'd be increasing most rapidly at this point, wouldn't it? What is this point? It's an inflection point, isn't it? Okay. So ultimately, we just want to know when does the second derivative equal 0 here is what it boils down to. Okay. So we can find the second derivative and then set it equal to 0. If we do that, 100 is going to be nothing. When we do this one, it's going to be pi over 2 times 20, so it'll be 10 pi cosine of pi over 2t. And this one's going to be 5 pi over 3 out here. It's actually going to be minus, doing the derivative, pi over 6t sine. Right, and then our g double prime, we multiply again, we're going to get 5 pi squared cosine, negative 5 pi squared sine pi over 2t. Just using the chain rule there. And then this one, if we do minus, multiply again, it's going to be 5 pi squared over 18 cosine pi over 6t. And again, we certainly don't want to use algebra to solve that. So if we probably just put it in my y equals and do my 0 command, so negative 5 pi squared sine pi over 2 x minus 5 pi squared over 18 cosine pi over 6 x. And on 0 to 8 is the question, right? Right. So with that, I guess the question is which one of those, if we see 3 of these answers here, which one is the correct one? If we find them, keep in mind that over here right now, I'm as I move to the right here, you can hardly see it, but ultimately now I'm below it here, and I'm above it there. You can see the cursor there. If I find my 0, whoops. There we go. All right. Looks like the first one there is 2.017. You notice that is an option too. Keep in mind, as we're going left to right here, we're going up. Okay, that would mean that the derivative is going from negative to positive. Remember, we're looking at a picture of the. This is the ultimate the function in question, and we want to know when it's a maximum or a minimum. Okay? And so by finding out when this is equal to 0, gives us the candidates. But the question is this the right one? If our derivative goes from negative to positive, that means that would be something like that, then, wouldn't it? So ultimately, that would be a minimum, wouldn't it, for our function? So that is not the one we want. So if we do our 0 command again. Whoops, I passed it, didn't I? Oh no, I'm still going up. Sorry. Still going up. There. Now we're coming back down. So now I can tell by the y value that I'm above the curve here at 7.8. I'll move it down below the curve. Go back up. And it looks like that one is 4.017. So 4.017. And that, actually that's not even an option on there. So actually, yeah, positive, negative, and then.
When it's decreasing this rapidly.
Oh, it's decreasing. Good call. I was thinking we're trying to find a max. So we are actually trying to find a min. We could try to find this one, but I'm assuming based on time we'll stop, but I assume that this one's not in the list. So the only one in the list would be the 2.07, 2.017.
Back.
Yeah, I'm going to collect that. I'll collect it back for me tomorrow. So just keep those for the time being. If you want to rework on any of the ones you got wrong, feel